This is Serina from the University of Brescia. Today I present a joint work with Mauro Vallati of the University of Anderson. The title of this work is Configurable Heuristic Adaptation for Improving Best First Search in AI Planning. It is one of the most prominent AI challenges. In the last few decades, a number of heuristic functions have been developed in order to guide the search process. Unfortunately, heuristics can get easily trapped in dead ends or huge search plateaus that drastically reduce their effectiveness. Starting from this scenario, we address the following challenge: allow heuristics to adapt to the characteristic of the search space in order to escape from plateau and dead ends. To address this question, we have made the following contribution to the paper. We introduce a highly configuration heuristic adaptation approach that can deal with inconsistencies in heuristic evaluation in order to dynamically adapt the evaluation of the HFF heuristic using best first search. The proposed approach is implemented in a high configuration adaptation mechanism in order to control the way in which the search space is explored and potentially avoid plateaus and local minima. We perform an extensive experimental analysis which demonstrates the effectiveness of our techniques on a range of benchmark domains. In the standard formulation proposed by Bylander, a propositional STRIPS planning problem is defined by the tuple where I is the initial state, G is the goal specification, capital A is a finite set of actions, where each action is defined by a set of preconditions, a set of additive effects that are a positive post-condition, a set of delete effects that are negative post-conditions. The results of applying an action A to a state S is defined as S plus the additive effects of A minus the delete effects of A if the precondition of A are included in the state S, and so the action is applicable. Otherwise, the state remains unchanged. A solution plan for a planning problem pi is an ordered sequence of applicable action that is able to transform the initial state in a state that satisfies the goal of pi. Complexity of planning problems, a number of heuristic techniques have been developed in order to guide the search process. A common approach for deriving a heuristic is to relax the current problem into a simple problem which can be solved efficiently. More formally, given a propositional STRIPS planning problem pi, the corresponding delete relaxed planning problem pi plus is obtained by pi ignoring the delete effects of its actions, A. The relaxed planning problem pi can be solved efficiently in polynomial time, and the delete relaxed heuristic value H plus of a state S is the number of actions of the relaxed plans pi plus. The underlying idea of our approach is to quickly identify the inconsistencies that can be present in a heuristic evaluation process and fix the behavior of the heuristic by changing the cost associated to the actions selected via penalization. In a nutshell, the point is to allow the heuristic to learn from the past to improve efficiency. First of all, given a generic function H plus based on computation of relaxed plan pi plus, we say that an action A determines an inconsistent evaluation of the state S, given a successor state SA obtained by applying A in S, if A does belong to pi plus and the heuristic evaluation of SA is greater than the heuristic evaluation of S. Or A doesn't belong to pi plus and the heuristic evaluation of SA is lower than the heuristic evaluation of S. In consistency evaluation occur, we update the penalization cost of A by a quantity which is proportional, essentially, to the value of the inconsistent evaluation. Here, the heuristic penalization HP is derived by H plus, adding the penalization cost of the actions in the relaxed plan. While lambda K, lambda R, which have values in the interval 0, 1, are used to define discount hyperparameters. And CA is equal to 1 if hyperparameter C is false. Otherwise, it is equal to the penalization cost of A. In addition, it is possible to set a maximum value associated to the penalization cost to a value proportional to the number of delete effects of the action. Here are the values that we have considered for the hyperparameter B. Note that the penalization costs are not only used for defining the heuristic cost of an element, but also during the relaxed plan computation for breaking ties in the selection process of the available actions. So they are able to modify the structures of the relaxed plan built during the search process. Given a neighbor element associated to a state S, with a hyperparameter A equal to 0, it is directly inserted in the priority search queue using H and the penalization cost, the penalization heuristic function HP. While when the hyperparameter A is equal to 1, the neighbor element is inserted in the search queue using H plus as primary index and using HP for breaking ties. Most algorithms have several free hyperparameters that can be adjusted in order to optimize the performance. Automatic algorithm configuration techniques use previously observed performance of different configurations and supervised machine learning, such as random forest, to learn a function f that predicts the performance of arbitrarily hyperparameter configurations. In a nutshell, an algorithm configuration system iterates first using the performance measurements observed so far to fit a machine learning model. Then it uses this model to select a promising configuration, C, to evaluate next configurations, trading off exploration in new parts of the configuration, space, and exploitations in parts of the state space known to perform well. Finally, it runs the configuration C on one or more benchmark instances and compares its performance to the best configuration observed so far. In this work, we employ the sequential model-based algorithms MAC, which uses random forest in order to find a suitable configuration for our hyperparameters. Now describe the experimental setting that we have taken into consideration. The proposed heuristic adaptation approach has been implemented in the well-known FF planner. 7 parameters have been exposed and allowed to control the behavior of the heuristic of our heuristic adaptation using a command line. We use MAC version 2.08 for identifying a domain-wise configuration of heuristic adaptation parameters that improves the part 10 performance of FF. The penalized average runtime per 10 is the average runtime where unsolved instance count as 10 times the cutoff time. Per 10 is a metric usually exploited in machine learning and algorithm configuration techniques, and it allows to consider the coverage and runtime at the same time. We focused our study on domains that have been used in IPC, International Planning Competition, and for which a randomized program generator is available. For our experiment, we created approximately 550 solvable random instances per domain and split them randomly into roughly 500 training and 50 test instances. Each configuration run was limited into a memory of 8 GB with a cutoff time for each instance of 300 seconds. table shows our experimental setting results in terms of part 10, percentage of solved problem, and IPC score. The considered planning engine running without the heuristic adaptation D, and with the adaptation, with automatically configured heuristic adaptation A. Bold indicates the best performance. Bold red stands for statistical different part 10 performance according to a Wilcoxon-Sagner rank test. Results in this table indicate that the use of the introduced technique, when appropriately configured, can lead to significant performance improvement in terms of part 10. In many of the considered domains, the difference, highlighted in bold, are statistically significant according to the Wilcoxon-Sagner rank test. Even in cases where the differences are not statistically significant, improvement can usually be observed. Performance are also generally improved in terms of coverage and IPC score. This figure shows how the compared system performs on the benchmark instances of the single travel domain. Instances are ordered according to the CPU time needed by FF with and without the adaptation heuristic to solve them. The default approach is able to solve only 14 instances out of 50. On the contrary, the use of the configured heuristic adaptation allows the planning engine to quickly solve more than 40 instances. Generally, the adaptation of the heuristic allows FF to be an order of magnitude faster. In this work, we have proposed a heuristic adaptation approach that can deal with inconsistencies in heuristic evaluations. Specifically, we investigated how to dynamically adapt the evaluation of the delete relaxation heuristic of FF using best first search. Our results show that the proposed heuristic adaptation approach can be automatically configured to deliver a statistically significant improvement on planner's performance, that it is possible to exploit a single configuration of the approach that improves the performance in a range of domains. Future work included evaluation of the performance when used with different heuristic and search strategies, and check whether different configuration of the heuristic adaptation can be combined into a domain-independent portfolio of planning engines. Thank you for your attention. Now I'm available for questions.